So we're going to step back a little bit in time and talk about, I don't know, whatever timeline you want to talk about, but we're talking about prebiotic chemistry, so before life. And I'm going to be talking today a little bit about how we generate molecular complexity. And when I'm talking about generating molecular complexity, I mean going from the simple molecules that we know how to make either on meteorites or in space or with Urey-Miller discharges to going towards these more functional biomolecules, so making proteins or RNA, but also, importantly, these membrane components. And so modern cells are really complex. And the membranes that compose them are also really complex. So in closures, we recognize that they're important for life. And modern cells tend to use phospholipid molecules as their membrane components, such as dipalmitoyl phosphatidylcholine, which is a typical lung surfactant. And so it's a really complicated molecule, but importantly, it's got a phosphate group and it has two long hydrocarbon tails. But if we want to start modeling these things prebiotically, we want to come up with a simpler model. And so people usually talk about vesicles. So vesicles, this is obviously not to scale, can encapsulate some water, and then they have a bilayer of membranes. So you have head groups and things like that. So you have surfactant molecules on the outside and water on the inside. And so membrane components are amphiphiles, they're surfactants, and so they usually have a polar head group and a nonpolar tail, and that means that if you're in water, the polar head group is hydrophilic, it likes water, and the tail group is hydrophobic, so these things will partition to the surface of water and orient themselves and concentrate in that. And we can measure this surface activity using a Langmuir trough, which is just a really simple Teflon dish. You put an aqueous substrate down, and then you can deposit a monolayer of surfactant on top. And then you have these little Teflon barriers, and you can squeeze the monolayer on the top and measure the surface tension. And by doing that, you can get a lot of the surface thermodynamics and orientation of the packing of the membrane in sort of a two-dimensional sense. So that would be a monolayer. But these molecules also form three-dimensional structures. They form especially once you get above a high enough concentration. So perhaps the simplest is a micelle, where you have the polar head groups on the outside and the nonpolar tails on the inside, and that is soluble, so it can float around in the material. You can also get the vesicles, as I said, where you have a bilayer with the soluble head groups on the outside and the tails in the middle. And you can also get things like reverse micelles or oil droplets where the heads are on the inside, the tails are on the out, and that will phase separate rather than be soluble. And so modern biology uses a lot of phospholipids, and they readily form these three-dimensional structures in vesicles, even at fairly low concentrations. And they have relatively simple phase behavior. They're not in equilibrium with the monomer in solution. They're kinetically trapped structures. But as I said, these are not very prebiotically relevant. So how do we get to a model that is more prebiotically relevant? So one of the most popular models that people have used have been these fatty acids, and specifically like decanoic acid. And so you've got a single hydrocarbon tail, instead of the double tail, and just a very simple carboxylic acid head group. And they've been used to great effect as modeling protocells. You can encapsulate RNA, you can do all of these things with that. But there's a fair amount about the phase behavior, I would argue, that we still don't know. So the generally accepted picture of the decanoic acid phase behavior almost entirely relies on the protonation state of that carboxylic head group. And so if you're below some critical concentration, which is referred to as critical vesicle concentration, critical aggregation concentration, or critical bilayer concentration, you're just going to have the monomer floating around in solution. But when you get above that critical concentration, it really depends on the head group. And so if you're at a really high pH, where all your carboxylic acid head groups are deprotonated, those are going to repel, and you're going to end up getting micelles. And if you're at a really low pH, where you're not at all, where everything's protonated, the head groups won't repel, so you'll tend to get phase separation into reverse micelles. And you get the vesicles in this sort of sweet spot in between the two, when roughly half the head groups are protonated and half the head groups are deprotonated. And these are also considered to be equilibrium structures, so you're always at equilibrium with a monomer in solution. So that's the general picture, and sort of one of the downsides to these is that you require a fairly high concentration. But if you look at the literature a little bit and you try to quantify this more in a phase diagram picture than a schematic, you run into a few issues. And so it's sort of the same idea. You've got micelles at high pH, oil droplets at low pH, and there's this really narrow range where you have stable vesicles, which maybe limits some of the prebiotic applications perhaps a little bit. And then there are also, if you look in the literature, several different critical vesicle concentrations that are reported, anywhere from 10 to 40 millimolar for decanoic acid, which is a pretty big range. And when you're making these vesicles, you usually make them in with some salt and some buffer, and that's not always very well characterized. So there's a little bit more in the phase behavior than I think people tend to accept. And there's also this range where there's this critical vesicle concentration, but the CRC solubility is only about 1 millimolar. So there's clearly aggregation happening in between these two, but that's sort of a disconnect that people don't necessarily talk about that much either. Yeah, so the role of salt and pH, perhaps maybe we should be talking more about ionic strength rather than straight up pH for how these things are going to do. And then just as an additional complication, I said the CRC solubility was about 1 millimolar. If you try to make a solution of it at 0.8 millimolar, you end up with a nice crystal at the bottom. So there's a lot of complications here. And so we sort of have these two options. We've got the fatty acids, which can make these things, but they're relatively fragile. They require very specific environmental conditions, and if you have too much salt, they'll fall apart. Phospholipids, on the other hand, are very robust, but they're almost too robust, because if you don't have the biological inclusions of modern life, you're not going to get much permeability and no exchange with information in the environment. And so we kind of want to look for something that's an intermediate solution between the two. So we want a balance between robustness and permeability, and we want a lower aggregation concentration than the fatty acids had. And so to do that, we have to come up with prebiotic chemical synthesis. And so when you're thinking about making things prebiotically, you need, and especially if you want them to self-assemble into a vesicle or a membrane or an enclosure, you need favorable conditions for both synthesis and self-assembly. And so people use an energy source. Hydrothermal vents are very popular. We use the sun, we use photochemistry. And environments, people talk a lot about clays and mineral surfaces. We tend to use the air-water interface because they were widely available in our relatively gentle environments. And so air-water interfaces, they're on the ocean surface, lakes, rivers, but also atmospheric aerosols. The surface area of aqueous atmospheric aerosols is about 2 orders of magnitude bigger than the surface area of the ocean. So it's an important thing to remember. And when we're talking about photochemistry, we've talked about how the early sun had more UV radiation, even though it was less luminous, and there was no ozone shield. So people often think about the UV radiation being destructive, but we would argue that it's not always destructive. Pyruvic acid, for instance, is a common molecule in today's atmosphere, as well as being pyruvate, metabolite, and it absorbs light within the solar spectrum. And we know the aqueous phase photochemistry really clearly. You excite it, goes to a triplet and pi star state, all this sort of stuff. But the main thing is you can make dimethyl tartaric acid. So you've gone from a 3-carbon molecule to a 6-carbon molecule. You've made a carbon-carbon bond, which is important. And so if we use a longer-tailed analog of this, 2-oxooctanoic acid, we can then go and do the same photochemistry and make a double-tailed surfactant, dihexyl tartaric acid. And so with water, sun, and this molecule, we've made a double-tailed surfactant, which is generally hard to do. Not a phospholipid, but a double-tailed molecule. And we do see that it's quite a bit more surface active after photolysis, which is good, or at least not at all surprising, because if you have more hydrocarbon tails, it should be more surface active. And yes, so the sort of schematic is, as we're doing the photochemistry, these molecules are going to start partitioning more and more to the surface. And without sort of our solution starts off clear, there are no micelles, we're below all the critical micelle concentration. And as photolysis proceeds without any further aggregation or whatever, the solution becomes cloudy. So we're forming self-assembling 3-dimensional structures during our photolysis. And we've worked on characterizing these. They're quite monodispersed in size. They're spherical, which we can see by phase contrast microscopy. They're small. They're only about 200 nanometers in diameter. But they're too big to be micelles. And they're very stable with time. And so we've tentatively characterized them as vesicles. Electron microscopy will tell us more. We're currently working on that. But in any case, they're self-assembling without further perturbation. And so for us, we're quite interested in how the role of the surface and what is the mechanism of the self-assembly. So the role of pH, as we saw with the fatty acids, we're more interested in the protonation state. Our photolysis mixture right now is quite acidic because it's just no buffer, no nothing, and so it's about pH 2.5, which is perhaps not realistic. But if anything, if you believe the model of the fatty acid phase behavior, working at a higher pH ought to be more conducive to forming vesicles. The role of salt is also really important, and just looking at how these guys self-assemble into these structures. And conceivably, if the photochemistry goes better at acidic pHs, atmospheric aerosols are quite a bit more acidic than the ocean, and so maybe the photochemistry is going to be more favorable in the aerosol, but then it would get deposited into the ocean and self-assemble into these vesicles. So there are a lot of open questions about this, but it's kind of a cool model system that's somewhere in between the two general pictures. And so with that, I'd like to thank everybody, and any questions?
Questions? Great, I gotta ask one. So you said one of the places, if I followed this, that these can form is in aerosols, and then they drop out of the sky and into the ocean. Is that did I follow that correctly?
The photochemistry could certainly happen there. You do see a lot of organic matter on aqueous aerosols that will partition to the surface. You usually think about that more as being a monolayer partitioning to the surface, but the aerosols are usually micron-sized, so it's possible these guys are small enough you might have a soluble guy in there as well. I mean, that's a speculation, but it's just interesting that you would get these different environments.
So I guess my real question is, do you have any idea of how photostable these are once they're in the aerosol and exposed to the harsher environment of early Earth, before they get shielded by the ocean?
So the good news, I mean, I guess I don't know if you had really high UV, but you've lost all your chromophores here.
Okay.
So you're not going to. So it's this alpha keto acid that's the key, and so it absorbs at about 320 nanometers. But here you've just got alcohols and acids, and so it's not a photochemically active molecule. I mean, probably lime alpha. I mean, you could smash it with something, but yeah.
Any other questions?
If you had other organic molecules in this mixture too, would that inhibit the formation of these vesicles? Would they get in the way, or?
That's a really good question. So with fatty acids, you can often stabilize the vesicle formation if you have a mixture. So even if you have a mixture of like a shorter-tailed fatty acid that won't form vesicles on its own, it will stabilize it. And certainly mixtures are going to be more prebiotically relevant.
Exactly.
It depends a little bit. So some people talk about shape parameter, and so if you have things that are of a different shape parameter for the self-assembly, that might be bad if they're not contributed. But one of the other cool things we're interested in doing, so with pyruvic acid, it forms this radical in the mechanism that I didn't go over, and it can actually be used as a driver to react with another molecule. So it's possible to perhaps use the radical formed with the 2-oxooctanoic acid and react with another lipid and then get even more a mixed double-tailed molecule or something like that.
Cool.
So there are a lot of possibilities.
Anyone else? All right, let's thank Rebecca again.